This is going to be a short presentation on the main equations from Chapter 15 about fluids. First, though, it's important to remember that fluids include not only liquids but gases. That's any substance that if you push on part of it, it will slide sideways rather than resist your motion. Like when water, if you sweep your hand across the surface of the water moves sideways, but the rest of the water does not. A fluid only exerts a force perpendicular to a surface that is confining that particular fluid. And we call that perpendicular force pressure which we calculate from force divided by area. Pressure originates in the collisions between molecules. Within the fluid, they just keep bumping into each other from all different directions due to random motion, so those forces are equal in all directions. But at a surface, when they can no longer keep moving but have to bounce off the surface, the derivative of the momentum during that collision results in a force that is perpendicular to the wall. So the force, which would be pressure times area, is always perpendicular to a surface. The symbol for pressure is P, lowercase p conventionally, but sometimes capital P, if only to avoid confusion with the symbol rho that shows up very often in what we're doing in this chapter. Pressure is defined as force per unit area, so it's newtons per square meter, but that unit is called the Pascal, which is described by two symbols, P and A together. So you have to write capital P lowercase a to clearly and unambiguously define the Pascal. P is also used for momentum. Notice that since momentum is a vector, the way to keep these two things straight is to put an arrow over the P for momentum, whether it's in one dimension or two dimensions or three. So that the arrow telling you it's a vector tells you that P is a momentum rather than a pressure. There's a few defined values that we use a lot. 1 atmosphere is defined to be 101.3 kilopascals. It's actually 101.325, but we don't use the last digits. We use the 4 sig fig value for all of our unit conversions in this course. Meteorologists like writing this as 101.3 hectopascals, so it looks a lot like 1,000 millibars, which is another name for an atmosphere. Atmosphere is also 14.7 psi, and it can also be written in terms of the unit called torr, which is millimeters of mercury. Just as a reference point, 30 psi tire pressure corresponds to 207 kilopascals. So the K, kilopascal, is a common unit. We very rarely use the very tiny units of pascals in this course. Pressure is all of the weight of a fluid. Atmospheric pressure is due to the weight of the atmosphere. For an incompressible fluid like water, the pressure difference is equal to the density of the fluid times the gravitational acceleration g times the depth that you are below the surface of the fluid. Writing this as P1 equals P0 plus rho g depth, that depth is y0 minus y1. Notice the way in which that's defined, so that the depth is a positive number when y1 is below y0. The symbol rho is a standard symbol for density, for mass density in particular, and the density of water is 1,000 kilograms per cubic meter, that is 1 ton per cubic meter. The reason you have to have a greater pressure is because the pressure from below has to hold up that little block of fluid that's shown in this diagram from figure 15.3 in the textbook. That extra pressure is simply due to the weight of the extra fluid above you. It's also the case that the larger pressure on the bottom provides the buoyant force on an object. As this picture shows, the force on the bottom of the object is bigger than the forces on the top, and when they sum up, they add up to the buoyant force that holds the object up. That buoyant force is equal to the density of the fluid, not the object, density of the fluid times the acceleration of gravity times the volume of the fluid displaced by the object. That would be the volume of the object if it's submerged, but just the displaced volume if it's floating. Again, density of water is 1,000 kilograms per cubic meter, and because water is effectively incompressible, its density doesn't change with depth, so we don't have to worry about any details like that. We just use rho as a constant. For air, the density of air changes with altitude in the atmosphere, so air, a compressible fluid like air, is completely different in terms of how its buoyant force is calculated. Fluid statics is based on an observation first made by ancient Greek that an incompressible fluid can transfer pressure and therefore force from one place to another. The observation that is called Pascal's law is that it's the pressure that's the same everywhere in a stationary fluid, at least everywhere at the same depth, And that leads to a formula where the pressure, which is force per unit area, means that force at place 1 over area 1 is equal to the force at place 2 over area 2. And in classic hydraulic systems, this gives a mechanical advantage. That's like a lever. A larger area results in a larger force. In this illustration from the textbook, which I've added some information on here, force F1 applied to that small area A1, whose area would be pi d squared over 4, results in a pressure at that point. That pressure is the same everywhere in that fluid that's colored pink. And on the other side, where it acts on an area A2, force 2, which is P times A2, is going to be bigger because A2 is larger. Larger diameter is going to be a larger area, so a larger force. And since the area goes as the diameter squared, the force ratio goes as the square of the diameters. Larger diameter, larger force. So you can amplify force. But usually at a penalty, like every other thing we do, work has to be the same. So if we take this force law from Pascal, where our F1 would be, say, bigger if D1 is bigger, or F2 would be bigger if D2 is bigger, where F1 is equal to F2 times A1 over A2, that if the fluid is incompressible, then the same volume has to be displaced at both points. And that's where we're really talking about hydraulics. Hydraulics actually comes from the Greek word hydro for water. If you have an incompressible fluid, then when you push down on one side, instead of compressing the fluid and increasing the pressure, you actually move the other object. So you can use hydraulics with an incompressible fluid to move things like brake calipers, robot arms, whatever it might be that you're interested in. And if the volume is constant because the fluid is incompressible, you get a second relationship that A1D1 must equal the volume equals A2D2. And that gives us an expression that the distance the first piston moves times the first force equals the distance the second piston moves times the second force. That tells us that the work input, F1D1, equals the work output, F2D2, so this acts just like a lever, exactly like a lever, where the force is amplified when you have a larger area, but that force has to act through a smaller distance. So that's the end of this. The pictures are all taken from chapter 15 in our textbook.